Hi CSD students, this is going to be a new recording on this time on the design of a chip based on Plan C2. Alright, so this, for example, is going to be a P3 exercise, an arithmetic circuit, and you know the many of them. We have adders, subtractors, multipliers, and for example we have here, down here in the learning materials, we have something like a comparator 1-bit. If you click in this comparator, what you see is the specifications of the comparator as stated in the plan A. We solve it in class, and here you are the full tutorial. So this time you've got another one, right? In the learning materials in this tutorial you have the same comparator 1-bit, which is going to be solved using the plan C2. Okay, so let's go on learning a structural design of a given chip based on this plan C2. So to make it easy, you see the circuit is the same as usual, a comparator 1-bit specifically. So this is the specification. It can be that short. Design a 1-bit expandable comparator, comp 1-bit, using the hierarchical multiple file plan C2 based on the method of multiplexers. And for example, let's take a MUX2 for generating the signal, the output signal GT, a MUX4 for the EQ, the equal, and a MUX8 to generate the less than signal. In this way, you will see how different MUXes can be managed together to generate a single multiple file project. So the starting point, you know, is the specifications, and the specifications doesn't have to change absolutely anything at all with respect the ones that we saw in class when we designed the same chip using the plan A. So you have a symbol, a truth table for this symbol, a 1-bit comparator with the data A and B to compare, the numbers, this time 1-bit only, and then the cascading inputs, the auxiliary inputs that you are going to use to go and rippling devices like that when generating a hierarchical multiple file architecture. So this table that you see here in the picture one is the one that was adapted from the chip, okay? The real chip is this one here, the 74LS85, for example, when you see the datasheet from Motorola. And this is an example of RTL, the result of our development, but this is the table, okay? This is the way people from Motorola wrote the table, okay? So we are going to invent pretty much the same circuit. So we have adapted the truth table, and the truth table is looking like this, you see? When the number A is larger than B, this case is for 4 bits, but it is the same thing all the time. If A is larger than B, what you've got, whatever the value of the GI, EI, and LI is 1 in GT, and 0 in EQ, and 0 in LT, and all the time the same way. And, for example, when the A is equal to B, what happens here is that, in this case, what is deciding the situation is the value of the auxiliary outputs, like in these 3 last rows, right? For example, if A is equal to B, whatever 1, 1 or 0, 0, what you've got in the case of GI equal 1 is going to be that GT is going to be 1, and this way, right? So this is the adaptation, and we have, you know, made some simplifications with the real table of the chip to make it easy. So it's going to be like that. In any circumstance, if everything is all right, GI, EI, and LI are going to be 1, only one of them. The other 2 are going to be 0. So 1, 0, 0, 0, 1, 0, or instead 0, 0, 1. That is going to be the case. So if this is the table, we can go back and then see the same table here in this simplified way in the picture 1. okay? Or we can see the same kind of information represented in time as a timing diagram, something that we'll retake later in the step number 4 when testing using a test bench, because, for example, we will set here the min pools variable or constant value, for example, to be 25.5 microseconds or something like this, and then we are going to organize all the test bench around this constant as its multiples. So, and the test, the test bench is just another way to verify that the truth table works as expected. So if this is the timing diagram, we can continue now orchestrating the plan, which is the key point here, because here is where the difficulty is lying. You have many options organizing plans. The plan A based on equations, the plan B based on hierarchical, hierarchical. The plan B is based on flowcharts or the direct translation of the truth table by means of some kind of artifact or a schema. But now let's talk about the plan C. And to make it a little bit more complicated than normal, you see, GT is going to be solved using a MUX2. But instead of using again another time MUX2, EQ is going to be solved using a MUX4. And finally, LT, the less than signal, is going to be solved using a MUX8. So plenty of opportunities for you to learn the whereabouts relating the method of multiplexers. So when you've got that in mind, these kind of specifications, that you have to draw something in a sheet of paper, like this initial idea. Okay? Again, I never will be tired to repeat that you cannot go to this section, which is a planning of the circuit, without understanding the specifications. So if something is still not clear in your mind, go back to 1, specifications. All right? Learn about the symbol, the table, the timing diagrams, see around some commercial chips, and learn, for example, from some books or other projects or problems, how to expand comparators, and learn from other plans, architecture. So you need some basics here to start something like this, right? So that's very important. And now is just the right time to talk about the general idea of this plan C2. And this is the layout. This is what we are going to expect here. If you put your attention here to this picture, it's very clear. You are with the aim of designing a comparator 1-bit, but using the method of multiplexers. So you are going to generate the 3 outputs, GT, EQ, and LT, using 3 blocks. Naturally, every block is going to be a component, something that exists, and it may be in a library of components, or, for example, as it is in digsys, in some place or another. The links that you hate that much, so you will have a link to find the chip 1, which is going to be a MUX2, naturally. You will find a link as well to find the MUX4 Vhdl file, and you will find finally another link to reach the file belonging to a MUX8. So you will require, as you see in this picture, and according to this method, 4 Vhdl files. Let's go repeating. The top one, comp1bit.bhd, then the MUX8, the MUX4, and the MUX2.bhd. And you know that the method is based on the position of these multiplexers here. So the output Y of the multiplexer is straight the output of the circuit. But there is a job to do here, which is organizing using logic gates and signals what is in the left. Okay, what is connecting, in this case, the 5 inputs to the channels and the selection lines of the multiplexers. That is what we have in mind. All right. So now that we've been reviewing the general idea and establishing a plan, we can go and find the equations. So you know that in this method, firstly, what you have to consider here is the expanded truth table. You know, this is the truth table in picture 1, completely expanded, combination by combination, okay, one by one to the end. So this is the table that you have to consider for this method. You know, it's a kind of a graphical method where everything has to be orchestrated around the truth table, but in full expansion. You know that using other methods, for example, the method of the coders, what you need is exactly the canonical expression using minterms or maxterms. This time, what you need in the method of multiplexers is the full developed table. And in this case, you see, it's not that simple. You have 5 inputs. So that's the only way to go. You have to go to the end from 0, 0, 0, 0 down to 1, 1, 1, 1. And if it's possible, in an ordered way this time. So understanding that this is the truth table of the circuit, now let's see how is going to be the organization of the truth table from this method of multiplexers point of view and just taking a MUX2. It's going to look like this. You see, let me explain it to you a little bit. Well, one of the inputs has to be used as a selecting signal for selecting the channel 0 or the channel 1. And well, if you see the table that far away, you see clearly here that, for example, the A input, the one which is in the left, has a value 0 for 16 positions and then 1 for another 16 more. So you see, so you can say that applying the A to the S of the 2-channel multiplexer, you can select the channel 0, and applying the A to the S the same way, when 1, you can select the channel 1 that way. So it is clear that this is, for example, a good decision to use the A as the selecting line. So now what is left here is the design of 2 sub-circuits, 2 combinational circuits, one for the channel 0 and one for the channel 1. So what is what you see here, for example? If this is what you've got in mind, you can very well use this picture. Only half of the table, because this is what is going to be the input of the channel 0 in the MUX. So if you have in mind the function gt, you have to use it like that. You have to inspect the gt from the 0, 0, 0, 0 down to the 1, 1, 1, 1 and see how this gt is going to be. And well, as you see in this cycle, there is a single one, because the x, if you like, can be whatever you want. For example, zeros. So if this is what you've got in mind, using the hexes, you know, the don't care terms as zeros, the gt becomes a very simple function that has only one term, b naught, gi and ei naught, and li naught. That's the function that you have developed here, that you can develop, okay? Only one. And let's inspect now the function belonging to the channel 1 in the same way, from 0, 0, 0, 0 down to 1, 1, 1, 1. And here, what you see is that the function has a lot of ones in many combinations. And if these x's are ones, for example, you can do that very well. What is left is just a pair of zeros, so only 2 terms. This is what is important here to see. You have only 2 zeros, so you can have a product of 2 sums, okay? So, and the sums are going to be, as you see, b naught, because remember that you are talking about zeros. This time, if you take the zeros of the function, you have to say that this is going to be a sum, not a product as before, but a sum. So this, and because it's 1, if you talk about sums, this has to be b naught gi you know, or EQ or LI not, because it's a 1. And then AND with another term, which is another sum. In the same way, B not or GI or EQ not or LI, like that, okay? So two terms. So this is the function that you have to apply to the channel 1 of this MOOC2. So, right, you can do the same thing, organizing the MOOCs4, the truth table for the MOOCs4, which is going to be like that, you see? Now the table is the same, but the subdivisions has to be 4 now, because you have 4 channels, okay? If you have 4 channels to think about, you have to select, for example, the A and the B as the selection inputs, okay? And now go the same way. For example, here you are a function of 3 inputs only, GI, EI, and LI. So the function EQ has a lot of values, but you can consider them all zeros except that one, which is a 1. So now you have the same thing as before, GI not and EI and LI. This is the function for the channel 0. But now if you keep an eye on the channel 1, zeros everywhere, so that is easy. And the same for the channel 2. What you have to apply to the channel input channel 2 is 0. And finally, the channel 3, it happens that is the same one as before. Okay, GI not and EI and LI not. That's the term. So you can use this term twice to drive 2 channels. And well, the same thing for the MOOCs 8. 8 channels now. And so the subsystem, the combinational subsystems left are even simpler. Look at this. The channel 0, well, you know that this time A, B, and GI are going to be the selection inputs for the MOOCs 8, S2, S1, and S0. So what is left here is the design of LT function for the channel 0. So what is what you see here? If this X is a 0 for you, and this other X down here is a 1, what you see now is a photocopy of the LI. So it is a buffer, you see? If you've got the input LI, the LI goes directly connected to the channel 0, because it's a copy. And if you now inspect the channel 1, what you see is a 0 everywhere. If you inspect the channel 2, it's a 1. The channel 3 is a 1. The channel 4 is a 0 everywhere for this function LT. The channel 5 is a 0. And the channel 6 is the same as before. If this X down here for this combination, it's a 0, because it's a don't care. You have 0, 1, 0, and if this X now is a 1 for you, you have exactly a photocopy of this function, which is LI. So again, another buffer. And finally, the channel 7, which is, if you are imagining now that the X's are zeros, you have 0, 0, 0, 0. So this is a 0 connection straight to the channel 7. So this is the idea here. So you can go and finally, you see, because now you have the equations and everything in mind and in paper, you can draw the final schematic that is going to look like this, you see? Exactly as we've been analyzing from this graphical interpretation of the truth table. MOOCs 2 channels and the corresponding subcircuits. One of them AND and another one product of 2 sums, something like this. Okay? And well, because this is going to be translated to Vhdl, you have to continue very well annotating every single name here. For example, this is a MOOCs2.bhd, and this is going to be the chip 1 of the circuit. The EL, the enable input active low, has to be connected all the time to 0. And you have here a black wire. You see, it is in black. Why? Because it's going to be an internal circuit, an internal signal. Okay, in one hand you have a port, GT, and inside, you know, in this box, inside to this architecture, you have a wire, and this wire is, it has to have a name. For example, G, and that one key, and that one down there for the MUX4, L. So you see the L is nothing but GI naught, EI, LI naught, what you've been deducing before. So the other channels go to corresponding values. Here S1 and S0 for this MUX4 becoming the chip 2 in this schema are just A and B. And finally the chip 3 is the MUX8 that generates the LT. Be aware, because now if you take the MUX8 that we've been using in previous examples, it also has an external, another output, YL, so you have to leave this YL unconnected. But unconnected means that has to be unconnected to a wire. So let's name this wire T. So you see, the input Li goes to the channel 0, and the same input Li goes to the channel 3. And then you've got here ones and zeros for the remaining channels. The selection S2, S1, S0 is nothing but A, B, and GI, as you have organized in the table, and that's the circuit. Okay? Yes, here you are some buffers and inverters, but that's not a problem for you. You may imagine, let's consider that, you know, the A and B and GI and EI and LI are nothing but ports. So you've got that thing. Ports, then some gates, some signals, and the final 3 chips. So this is digsys, you know, discussing about an schema. This is what you have to do all the time, discussing schemas. And as you can imagine, this is what I'm asking you once and again. Please do not write anything in Vhdl if this schema is not yet finished. Finished means to the end. Think about every single wire and make it and give it a name, okay? If you've got a wire here, it has to have a name. If you've got another wire here, it has to have a value, 0 or 1 or a name, right? Like this one here. This component has to be connected somewhere, the outputs. For example, the Y is the LT, but the YL has to be connected somewhere else. For example, a wire in the air, right? You will get a warning from Quartus Prime, but that is not a problem. It's just a warning telling you that here you are a signal that is in no use, but you know it's a warning, it is not an error, I mean. So, well, you see, this is the perfect, you know, photocopy I like you to do by yourself when talking about designing a Plan C2. Okay, and a schema. So that's, if you've got this schema, I insist you can continue. If you haven't got that schema, you have to keep trying until it works for you. Okay, so once you've got this schema, you can go to the next section, which is going to be the development of the project using EDA tools. Okay, and that's the way it works. So if we go and start the next section, developing, you know, well, the aim now is different. We have to organize a project in one of the EDA tools from Xilinx, Intel, or Lattice. For example, let's use Intel Quartus Prime. So the project name, you know, the project name, this is known. It's a comparator 1-bit. And the project location is the same. You will go, for example, to the virtual desktop Rabara, and there you will invent in your L, you know, your personal drive, Samba drive, you will invent in the right location, because this is an arithmetic circuit, P3, you will invent here this comparator 1-bit, and now it's time for inventing a name for the folder. For example, why not? Comparator 1-bit, you know, Plan C2, and Plan C2 specifically using the method of multiplexers. Because, you know, you can invent the Plan C2 using the method of decoders or any other combination of circuits and blocks. So this is what we've got in mind. So what goes next? Yes, the translation of the plan above, this final schematic that you see here, to Vhdl. And here you are in this web, the circuit completely finished. All right, this is the top entity already finished. And you know that the project has as well many other files. For example, the MOOCs2, the MOOCs4, and the MOOCs8, which has been taken from previous projects in P2. Okay, so you can reuse them. So here you are the link. So you know you can go saving them all as. Okay, so our aim, once the project is finished, is to inspect the RTL. And the RTL has to look like this, for example. Pretty much, what we've got in mind in our sheet of paper. You see, 3 chips, the wires, some gates, and the like. So, all right, if you've got such an RTL, such a register transfer level schematic, that's okay, because it means that practically the Quartus Prime has understood your ideas, and your schema that, here is in paper, has been very well captured by the machine, and now it's a computer idea. Well, it's an idea that has been translated to a computer tool. And now it's a circuit. You can accompany this RTL, observing how it's going to look like the technology view. And finally, if you like, the next step, the fourth and the last step in this series, is the validation, the final testing. And we do that all the time in the same way. And because this example is the same as you had before, you see, if you go back to the P3 learning material, you already have, the comparator that you are now inventing solved previously with this other method, the plan A. So why not? You can go to the plan A, and because now you are talking about testing, you can go straight to the testing and reuse. You see, you can reuse exactly the same test bench, because the architecture means nothing for the ETSU, which is related to testing devices. You are testing entities. Whatever it is inside of the entity is not the problem of the test bench. The problem that you are going to solve testing by means of a test bench is the test of the component, not what is inside. Inside the component, you can have 20 different architectures. So for the 20 of them, you can use the same test bench. So this is what I did here. I just copied the file and pasted it in the same place in the other tutorial. You see, in the same tutorial using the plan C2, if you click here, down there, finally, in the testing and validating the design section, you have exactly the same test bench. Naturally, if you like, you can go and modify it. For example, adding all the possible input combinations. But to start, it's okay to take the same test bench from another similar exercise. Okay? Okay, so let's continue. Now focusing our attention in the developing of the project, step by step. And in this way, we will consider this time that the files that you've got here, the source files, the 4 of them, do not exist. They are here because it's a tutorial and you simply have to click them to get them. But imagine now that we all have to start this from scratch without having this file. So the point is where to get them and how to write them, okay? Because the components can be easily taken from previous examples, but what about the COM1, which has to be the perfect translation of this final schematic that we have in paper? Well, so let's see the way we can do it in real time, and in this way you can have an estimation of how long it may take to finish a project like this. Well, in order to start, you better go and switch to Rabada, because now the idea is to use EDA tools. So you can go and switch your laptop to the Rabada environment, just generating a full screen. This is better. So now we are in another computer in this presentation. So here we are the same digsys. So we go to home and we go down to P3 and we try to find here the location of, for example, some muxes. And I remember that the muxes were something that we deduced in the project 2, precisely the mux 8. And, well, this is a structural plan based on plan C2. So in P2, the mux was solved using the plan A and plan B. So why don't we go to P3 itself and just go down to the learning materials, because it's going to be about muxes, you see? So here in the lab 4, the other day in class, the lab 4 was about the design of the mux 8, precisely, but by means of this tutorial, which was the mux 8 as something structural using the plan C2. So this is what may be taken this time as the sheet to be copied and pasted and modified. So for example, here, if you go down to the file section, which is the developing of this MOOCs, down here you have, the MOOCs 2, the MOOCs 4 that you need now, and as well the MOOCs 8, which is at the same time something structural like this, you see? So what is going to be the difference? No difference at all. You are expecting in this comparator 1-bit to generate a schema like this one that you see here in the picture 3. So why not to use the same MOOCs 8 VHD to copy and adapt? So that's the point. Let's just start with the MOOCs 2, and this is save the link as, where exactly? Where? In your L, CSD, the corresponding P3, and here, a new folder that is going to be comp 1-bit 2C plan C2, and then the method of multiplexers. That is going to be the destination. So let's place the first component here, then the next one, the MOOCs 4, save the link as in this exactly same position, save. And now let's save the MOOCs 8, because that's the other one that we will use, remember, for building the function less than. So let's save the MOOCs 8 the same way, save the link as the MOOCs 8. And now let's switch off for a while the Firefox browser, and let's go to the directory section. And here you are, the L, CSD, and P3, and your new project. So here you are, the 3 components of our design. Remember the design that we have to translate. It's a good thing to have it in hand very well, because that's the point. Translate the schema. You see, I'm insisting all the time in this, because in this way the Vhdl will never be a problem for you if you have the schema on the side in front of you. So let's go to the P3. This is where we are now, P3, in the learning materials, and solving the comp 1-bit using the method of multiplexers. So down there, the final point and discussion of the plan was this final schematic. So this is what exactly we have to translate to Vhdl. Okay, so let's go and see how it works. The MOOCs 8, you see, for example, the MOOCs 8 looks pretty much like that. MOOCs 8 entity, and then, several components. So this is a good thing, because the components can be modified now to generate the comparator. So let's switch down these MOOCs, and let's copy Ctrl-C and Ctrl-V, and now let's rename it, okay, as comp 1-bit. This is the top entity now. So now let's just start editing this file, and let's see what we can do. Let's just thumb the file. So an example of a chip design. This is not a MUX, but it's going to be a comparator 1 bit. You see, take it easy. Take it easy, and you know, if I'm paying attention to the commands, you have to do the same. Comp 1 bit. Okay, the comp 1 bit, that goes fast using plan C2. And the method of, or the method of multiplexers. So comp 1 bit, a structural using components, edge size p3, that's right. Okay, if you like, you may say such a thing as a translation of this file, of this schematic. And now it's time for annotating here the source file. So the source file is this, Control C. So that is what we are going to do here, the translation of exactly this picture into Vhdl. So the library section is okay. This is not going to be anymore the MUX8, but the comp1. Well, it is the entity, right? So why you don't have to do that now. You can copy it from the other tutorial. So let's go back to the web. Digsys P3. We have this chance, right? We have already this circuit here as a plan A. This means that the file exists. So the planning of this circuit is already here. So this is the circuit. So now you can go, you see, and copy the entity section, Control C. So now you can go here and paste it. So that is going to be the component to design. The entity, the same library and the same use. So now the architecture, it's going to be like the MUX, hierarchical architecture. You may say plan C2. And now you can copy this, Control C, down there. And, you know, plan C2 architecture. So not a MUX8, but the comp1. So Control C, Control V. And now what? Well, the component MUX4 is used. Very well, so leave it as it is. And now you need another component some way. So make room here to locate and find the MUX8, which is in the same place as you know. So the MUX8, you can edit it using another file, you see. And now you can copy the port section, Control C, because the port section is the description of inputs and outputs, and this is not going to change. So place the port section, and now copy this end component, Control C, Control V, and then the component MUX2. So this is going to be the component MUX8. Right, so the 3 components are here. What else? Now it's time to keep an eye on the schema. So let's go back to the schema. And apart from the chip 1, chip 2, and chip 3, we need here, we require some wires. For example, the L, you see, the L, the J, and the key, and the T. You see, down there, you've got the T. So, key, J, L, and T. Those are the 4 wires that you need in this application. So now it's time for you to begin. The MUX 4 is okay. It's not going to be the chip 1, but the chip 2, I guess. Let me go back. So it is the chip 2. The chip 1 is the MUX 2. So you can go and say that the chip, you only have one chip 1, so you can say that this is going to be the chip 1, a MUX 2. So now you have to delete something here, like the channel 2 and the channel 3. You can leave it by now like that. Because it's the channel 2, you only have S, not a vector, but a single wire. And then you have to have the chip 3, and the chip 3 is not a MUX 2 but a MUX 8. So now is your turn to copy, for example, something from here, like the MUX 4, Ctrl C, and paste it here like that. So the chip 3 is going to be the MUX 8, and the MUX 8 is going to be a channel. So make room for adapting now the channel 7, the channel 6, the channel 5, the channel 4, the 3, the 2, the 1, the 0, and now the S, remember, is 2 down to 0 because you have to select 8 channels. Okay. What else? The equations. So let's go now instantiating the devices. For example, the chip 1 is the MUX 2. So now it's time to see that the EL is 0, that's all right, but the channel 1, I guess it's the J or the key, and the channel 0 is the signal J. S is A, I guess, it's the input A, and Y is not P, but the output GT. So I guess that this is the signal or port where every single input and output of the component MUX 2 chip 1 is connected. And you can check that here very well, because it's nothing but this. You see, the channel 0 is J, the channel 1 is key, S is the input A, as you see here, the Y is GT. You see, I've got a mistake here, the Y is missing here. I will elaborate that later. So now you can focus again the attention instantiating the chip 2, as you see in this picture. So the chip 4, I mean the chip 2, which is a MUX 4, so EL is the same, 0, channel 3 goes to L, I guess, the wire L, channel 0 the same L, and the channel 2 goes to 0, and the channel 1, I guess that it goes to, well, I will now verify that, goes to 1, and then you have a MUX 4, which is the selection down to 0, but not like this. It is going to be something like this, because they are individual signals. One is A, and another is B. Control C. So you've got here S1 and S0 as the pin name. So once you've got the pin name, you have to connect the S1 to A and the S0 to B. And the output doesn't go to key, but it goes to EQ in this application. So let me check again if something is wrong or something that is not like that. The channel 1 goes to a 1, and the channel 2 goes to a 0. And the channel 3 and the channel 0 goes to the wire L. But the channel 1 goes to 1. Channel 1 goes to 1, and the channel 2 goes to 0. So perfect. You see, there is not a difference now. And this is the instantiation of the chip 2. And finally, the chip 3, which is a MUX 8. The E is active all the time, you see, you may say so. And now the channel 7, well, let me see, I guess that goes to 0, but I'm not sure about that. Let me see the picture, because you see, it is exactly a perfect translation. Without this picture, you can do anything at all. So, the channel 0 and the channel 6 are connected to Li. The channel 6, Li input, and the channel 0, the same Li. Now the channel 07, the channel 5 is 0, I guess. The channel 7, 0, the channel 5, 0, the channel 4, 0, and the channel 3, 1. Channel 4, 0, and the channel 3 is not a 0, but the opposite of 1. The channel 2 happens to be another 1, and the channel 1 a 0. So the channel 2, another 1, and the channel 1, another 0, as the channel, no, the channel 0 is Li, very well. So now the output is not key, but the output is LT. Remember that we are inventing a less than function using a MUX 8. And finally the selection. So let me copy this 3 times, and let's arrange the connections, because we know very well where the connections are. For example, S2, I guess that this is the most significant selection input, and this goes to A, colon. Then the S1 goes to B, colon, and the S0 goes to GI, colon. So this is S1, and this is S0. Something like that. You see, it takes a while to convert your schema to this organization. But I guess that this is all, right? So now you've got the 3 MUXes instantiated, every one of them with the corresponding name. And now the only thing left here is the 3, or well, the wires, you know. For example, L is nothing but L, it is simply what you see in the schema. So let me show it to you. L is this function from the inputs. GI not, EI, and LI not. So this is not GI. Remember that this language is pretty much Wolfram Alpha. So not GI, and EI, and not what? LI. And now semicolon, because this is the way in which you are instructing the machine to invent some gates. So this is the L, as you see here in this picture, and now it's your turn to orchestrate the G and the key. But I see that I forgot something. You see, the MUX 8 has another input here. The MUX 8 has another output, sorry, YL. So let's do that now that I remember. So you see, you've got this, but you also have to add another output, which is YL, and this YL is connected to the wire T. Now that is finished, okay? Yeah. So let's continue with the equation. The next one is going to be J, and J happens to be B not GI, B not, so not B, and because it's a product, GI, and then I don't remember, EI not EI, and not LI. That's the equation, semicolon. Okay, and finally this is the J, one term, because remember it was a single one in the table. So that is what was the Y away, J, and L was the same, a single one. But now what is left is key, and key is 2 zeros, you see? So this is 2 zeros in the table. I remember that. 2 zeros. Which ones? The one that you see here in red, key is B naught, GIEI, LI not. Let me see if I remember it. Not B, okay, or, because it's a sum, GI, or EI, or not GI, something like this. And now because you have two sums, you got to use a bracket here, and this is one term, one sum, and now a product, and the other one. But the other one is pretty much very similar, so let's copy, Control C and Control P. And now not B is the same, GI, and here I guess that this is not EI or LI, a buffer. So nothing else is left, semicolon. So now you see you can delete anything else that is left in this file, and I guess that is nothing left. You see, one sum and another sum, not B or GI or not EI or LI. Let's have a last checking of this. B not, GI, EI not, and LI. Exactly this equation. Now it is written in Vhdl. So I guess that that's the end of the translation of the schema. I don't see anything else to say or to do. So let's go back to the beginning, just keeping an eye on this. Well, if you've got some typos, for example, if this semicolon is left, well, the Quartus Prime will detect that and I will tell you. So probably if you've got some mistakes, you can repair that very well and easily. The point is that there is nothing to invent, and I see some people asking questions only focusing on the RTL directly without this huge idea, the main idea here, which is just a simple translation. So you see, I'm not worried about anything about Quartus Prime, because what I'm typing is simply a translation. Okay? So once you understand this, you will do that 1,000,000 times without a problem. So S goes to A, here S1 and S0 goes to AB, and here A2, 1 and 0 goes to ABGI. The other functions are depending on the remaining outputs or inputs, and that's all. So let's see if it works. Okay? So this is what is going to be called COM1B solved by the method of multiplexers. You say yes. Let's save that one again. So now you can switch to the tool. So you see, you can set aside the browser, and now this is your folder with all the files required. Remember that you later will copy as well the test bench. But now it's time to synthesize and finish with the development. So we will just go to the desktop and run Quartus Prime. Let's see how fast is it here now, these days, in this environment. So this is the Quartus Prime Lite Edition project navigator. You can switch off the home window. You can make room here. Okay, so you have nothing yet here. So now it's time to go on File and say New Project Wizard, which is going to be next. And the project wizard is going to be the location, you know, is going to be your L CSD P3 and exactly this name. Select the folder, and now you know that the name of this project is comp. The synthesis project is comp 1-bit PRJ. But you also know that the top entity name is the comp 1-bit. So you say next, empty project, next, and now add. You see, if you say add, because you are pinpointing the project folder, the 4 source files are detected in any order, but what is important is that all of them are detected, and you say next. And now it's time for the cyclone. Remember that this time the cyclone is the one in the board D2. So I remember which one is, but if you don't remember, you can do that again using the web and going to the, let's find a target chip for this project, which is going to be, for example, an Intel board, the one that you see here, the Thoracic D15. So this is the chip. You see, EP4CE 11529 F29. So this is the chip that you have in mind to use as a target chip. So let's type that something here, for example, 115 and F29, not 27, but 29. So you see exactly, this is the chip that you like to use. So you say next. And now everything is from Intel except the tool used for simulation with model is from Mentor Graphics, Altera Model Sim. And now the project is going to be Vhdl. So you say next and finish. And now the machine is composing the project. It's trying to see if everything is fine. So you see, you have files, the 4 of them. It's a multiple file project. You have the 4 of them. And then if you see, instead of the file, the hierarchy, well, it is not yet generated, the hierarchy. You see, it's a single item, the top one. So now is the turn of start the compilation. And now it's time to see if everything is fine with the writing of all the files. The 3 components has to be correct because they are from previous projects, so they are like if they were in the library, so they have to work fine. But we don't know anything about the comparator 1-bit top entity. So the analysis looks right. And the machine continues with the execution of the full, and this is called the Vhdl design flow. You see, it is analysis of the source files and synthesis of the circuit so that you get in the end the net list, and the net list that we are interested in is the RTL. But you know, the machine tries to go to the end, which is a fitter and place and route for this chip, the target chip, and then there is an assembler of everything, generating the configuration programming files for the chip, and then you know you have as well a timing analysis and an EDA netlist writer, and that is what we are going to use the next day or the next session when talking about gate level simulations. But for now, you see, our simulation is just here, because what we are going to simulate later in the next step is simply the Rtl Viewer. So if you click the Rtl Viewer here, or if you do not remember that, but you can go to Tools and do the same job of reviewing the Rtl schematic. So this is what the machine is going to invent for you, right? So perfect. It looks right. You see? So now is your turn to what? Well, for example, to take a picture of this. If this is right, you can capture this picture. Okay? That way, you can go and capture this picture, take a photo, and now is your time to add something like task. Like it seems all right to me. Okay? Whatever. You know, an indication. You see, this is the wire L. Okay, whatever. So for example, here, you see, you may say that down there, you don't see the why not. So you can just annotate that thing. The why not is not here. With a text or with a pen. The YL is not used. Very well. So this is the task that you have to go doing here. And then you take a picture, and this is for your records. Okay? Not only the printing of this, but the printing and interpretation with your own language. Whatever you have to say about the circuit, so please go like that. Annotate. This is what we want. This means that you've run the software, and in some way or another, you've been able to analyze the circuit. So, for example, I see here that I've got my two sums and a final product. So this is exactly what I'm expecting for the wire key, and the same for the wire J, all right, or L. A product of 4 inputs, and here a product of 3 inputs. This is what I'm expecting, and the output of every multiplexer with the right reference, chip 1, chip 2, and chip 3, goes to the corresponding output. And every channel is connected to somewhere or another. So it looks fine. So now, you know, it's time for saving this picture. And a picture like that, if you have to save it, naturally, it has to be in the right portfolio. So save it as, you know, the picture RTL in the right place. So file, well, whatever, you save the picture in your way, because here, you know, I'm switching between computers, and well, that's the picture. So you can now switch off this window, and we can continue. So the next step is the step of testing. So what is required for testing? Remember? So for testing this chip, what is required, you see? So you may say, okay, to developing, so you can go to the next section, testing, and here, you know that what is required is to pay attention to the test bench, because in this test bench, we are going to translate now into Vhdl, not the component and the test, the one we have just finished to develop, but the test bench, and I mean the timing diagram. This is what we are going to translate into Vhdl. But, you know, that job is also automated. There is a kind of an automation here. Well, because Quartus Prime, you know, is able to generate for you, you know, a processing. You can start a task, and this task is for, you know, the component 1 bit. You may say processing, start what? Start a test bench template writer. So if you say so, you are generating a template or a skeleton for very well following with the testing of the chip using a test bench. So this test bench has been solved. You see, you know the position of this test bench. It is down there into your project folder and simulation model sim, and we will do as always. Take it, copy it to the root folder of the project and change the file extension and the name. So, right. So now it's time to do so. So this means to go into simulation, model sim, and now we've got the file that we have interest in, Control C, and we place it up there, 2 folders ahead. Above, now you have component comparator 1 bit, test bench, and this is Vhdl. Okay, yes, I want to change the file extension. I can examine the file now, okay? But I will do that. Well, why not now? Now is a good time to do that, because if I open now this file, I see that is a kind of an automation. Yes, this is the box of the test bench. The test bench entity name is comparator 1 bit Vhdl tst. And here you are the architecture that you understand very well now. Some signals to connect the component and the test. Okay. And the instantiation of this component and the test that these people call EI, you see. I1 is the name, is the chip or the unit on the test reference name. Okay, I1. And then, you know, you have an init process which is for nothing, which is empty. So you will delete that. And then you see here another process that is empty as well, so delete that. So let's make room to copy our process. And here you know that after the component and before the begin, you also have to pay attention to the sketch of the timing diagram, because it is something like a min pulse variable that you have to adjust to a given value. So everything is going to be related in time to this constant. Okay, so now it's time for doing this thing of going to the naturally, don't do that from scratch, but you know, go to the right place, testing. And here you have an example of testing. Precisely, you are inventing the circuit now. So go to the constant section, Control C, and paste it into the right place here. Okay, on 25 or whatever. So this means that, for example, in order to run several vectors, for example, the 32 of them, 1000 microseconds is okay. And now the stimulus. The stimulus is the copying, you know, copying the signals, the input signals. So you go back to the web example and you have, you know, the idea now of taking it all the test bench, which has activity for all the signals, not all the vectors naturally, but some of them. So you copy all this signal, Control C, and paste it in the right place, that way. Alright, so you see, because the entity names and everything has not changed, you see the importance of not modifying never ever the name of the signals. Okay, the name of the port, sorry, because in this way you can go from project to project, taking advantage and copying and pasting. Because, you know, the test bench is the same all the time. So here you are, a test bench, name TV. This process consists of injecting into the circuit a stimulus at different times. First of all, you input, for example, 0, 0, 0, 1, 0. And this situation means that equal has to be 1, because the two numbers are the same. So if the two numbers are the same, accordingly to the two table, because those are the auxiliary cascading inputs, 0, 1, 0, this means that this is equal, so equal, 1. And wait for, you see, you keep this stimulus for a while in the circuit, and then you apply another one. This time, two vectors which are the same, but now the value is 1. And you have the same kind of inputs, so you have to have the same output, EQ equal 1. then what you do is to input a number, for example, A larger than B. So this means GT equal 1, whatever the values, you see? So you can go and say that these, in this specific stimulus, these values are don't care, okay? You don't have to worry about these values because A is larger than B. And so on and on and on. You see here the same thing. These values don't care either in this next stimulus because here you are representing A less than B. So this is the corresponding output that you are expecting. And so on and on and on. Okay. You also can generate here signals that has no interest. For example, this one where A and B are 1 and 1. So the truth table is going to be depending on the previous signals. And you see, it looks like that something went wrong because 2 of the auxiliary signals has a 1. So this is an unpredicted situation. If this happens, it's because something went wrong. So you see, in this case, whatever is going to be in the output, it's not important because you won't care about, okay, this output because it has no meaning for you because this situation is not possible and so on. So until the end. So you see the job that is associated and the time that is associated into translating the test bench into a test bench, the timing diagram sketch. So this is the time, more or less, more than quarter of an hour. So you can now say save everything, and now you can go back to your folder, and you see the folder that you are editing here is like that one. So everything is all right now. And now it's time for going back to Quartus and launching, you know, a tool which is precisely the test tool, the RTL simulation, which these people from Intel has agreed to mentor graphics, and this tool is Model Sim. So now the machine just go and generates a new window where you are going to start again a new project. Okay, so let's do it. We know exactly what we want because it's all the time the same, you know, a new project. Let's fetch the project location. The project location is the same as usual, you see, so comp. And now the name of the project is also known. So comparator 1 bit, but now you know that you are performing a functional simulation. Let it be like that. Comparator 1 bit functional simulation. And the library where the machine places all the stuff is work functional, because the next day we will solve a work gate level, but now is a work functional. So you say okay, right? And now you only have to go and say add existing files to the system. Which existing files? Well, let's browse all of them. You see, this simulation will consist of that many number of files. 5. The 4 belonging to the unit and the test and the test bench itself. So open them all and say okay. So all the files are, you know, added to the system. You can have a full view of this model sim. You see, you have to switch off the add window. Now it's okay. So you see, you have question marks in the file because they are not yet analyzed or compiled or understood. So now is your turn. You go to compile all, and the machine will try to interpret everything here. So perfect a green mark everywhere. Everything is successful. So now is your turn to go to simulate. Simulate, start a simulation. And what is what you have in mind to simulate? Well, the work functional that appears here. So precisely not the comp 1 bit. You can do that if you have another test bench. But now is not the time for the comparator 1 bit, because this is precisely the unit and the test. What you are simulating here is the test bench. This one, comparator 1 bit VHD TST. Remember that was the entity. So you say OK, and now the machine will start the wave display. So everything looks fine. So now you go to the hierarchy, and you go to add to wave, all items in region. That's okay. So you see all the signals at this level of the test bench are going to be placed here. You can make some room here, and the important thing is to see the name of the variables. You see the variable A, B, EI, EQ. You see they are disordered. So now it's time to add, for example, a new divider. You may say outputs, right? A divider. You may also say which property of it can be, for example, 40 pixels wide or something like this, and you can start moving the outputs to this side of the divider and place them in order. You see, EQ goes here, GT, EQ, LT, and now the inputs A, B, GI, EI, and LI. That's the thing. So now what is left finally is simply go and say run, for example, 700 microseconds, just to leave space and leave time for the simulation to rule the full section of the full range of stimulus. You see, so the machine has finished it. So now you go and select the wave and zoom all, and here you are, the results. So now finally is your turn to do exactly the same thing. You can go and review what happens here. For example, what is what you see? 0, 0, 0, 0 means that the two numbers are the same. So if EI is 1, the same with EQ, okay? You can go to the next stimulus. The next stimulus says something similar. 1 in A, 1 in B, and then EI is high, meaning that perhaps the previous comparator is giving you this output, that the previous numbers are the same. So what is the result? EQ equal 1. So perfect. And so on and on and on. For example, this time you are checking A equal 0, B equal 1, GI 0. So the three values here are not important, because if this is 0 and this is 1, you have to have and say that what? Something went wrong. You see, A 0, B 1. So the output has to be LT equal 1. And you have a problem here, okay? So let's see what has happened. You see, this is what I mean by reviewing the chip and the test and paying attention to the result. You see, what I'm doing here has nothing to do with copying and pasting this graphic from somewhere else. You know, if I go reviewing the vectors, sometimes I see mistakes. For example, the comparison now is okay, but this time the comparison is wrong, because you have 0, 1, and you have EQ equal 1 and LT equal 1, and this cannot happen. It doesn't happen. It cannot be like that, never ever. You cannot have two outputs high at the same time in any situation. So you have to see what happens. Perhaps if you go exploring the next one, you see you have 0, 0, 1, 0, 0, and here it's okay. But the next 1, 1, 0, 0, 1, okay, this is okay. But you see, I see that perhaps I've got a problem in the EQ. Is that so? EQ or LT? One of these outputs is wrong, okay? So I've detected a problem here. So now it's time to go back and analyze again from the quartus itself what has been happening here, okay? Because the test is not ready yet, you see? So we have to go and explore again the file to see what went wrong with the transcription of the schema into the Vhdl, because something is wrong clearly, you see? Two signals high at the same time. So now it's time for stopping the simulation, okay, and going back to the quartus prime and try to find the error, you see? So probably is an error in the connections that you've got here. So if I click the comparator, I can check. You see, there is no syntactical errors, but you know, you have a logic error. So those are the three muxes and the signals. It looks right, but then something went wrong here. EL0, channel 1 goes to key, channel 0 goes to GA. So now it's time to go to the web and pay attention to the... So you see, this schema is not right at all. So there's something left here. So GA is channel 0. Is that right? Yes. Key is channel 1. S is A. So let's go down. You have to review the connections. It's like if you have a proto board and you have changed the position of something and the circuit works sometimes and sometimes not. So now you see you have to review that channel 1 is 1 and channel 2 0. Yes, this is okay. LL, A and B, EQ, that looks fine. Okay, so let me see the last one. The last one is S2, S1, S0, A, B, and GI. A. The last one is this. A, B, and GI. Channel 0 is LI, channel 6 is LI, and then you have channel 7, 0. So the 7, the 5, and the 4 are zeros. The 7, the 5, and the 4 are zeros, and the 3 and the 2 are ones. The 3 and the 2 are ones, and then the 1 is a 0. So it looks right. There is, I don't know what is happening here. Perhaps with the equation of this L. Okay, let's review the equations because the connections looks fine. So the equations are GI naught, EI, LI naught. L, GI naught, EI, and LI naught. Then the J is a single term, which is B naught, GI, EI naught. So this is not B, GI, not EI, and not LI. So it looks fine, the same. So finally, key. So what about key? Is B naught GI, that's B naught GI, not B or GI, and then is, you see, EI and not LI. EI and not LI. And what? Not B, GI, not EI, and EI. So everything is fine. So where is the mistake here? Who knows? Now it's a complication, you see, because the chip looks fine. So what is happening here? You have A0, B1. So this has to be less than. So what is happening with the EQ? EQ has something wrong. And what is this EQ that is wrong? Okay, channel 1 is 0 and channel 2 0. So I guess that this is okay. So everything looks perfect. So we have to go back to the truth table. Let's see if we find a mistake in the truth table. It's something related to the EQ, which is not working fine, you see? So if you've gone through everything and everything is all right, you have to go to C and check that everything here, for example, the connection of every channel is correct. Okay? So let me go back, or let's just, in which way I can do that? Just a new window, digsys, because you see you have to go comparing things in Windows, or you can print this stuff, which is better because you see what is going on fastly, right? So you can go to P3, this tutorial exactly, and this tutorial was the comparator 1 bit, and we have to investigate what happens in the table of the EQ, I guess. So here, so let's, I've seen it. You see, the channel 0 is perfect, this term. The channel 1 is 0, and the channel 2 is 0 the same. You know, that here is the problem. You see, the channel 3 is the same term. So I've detected the error, because you see the channel 1 is 0 and the channel 2 is 0. So the mistake is here. You see, the channel 1 is 1. This is an error. So I will go and correct now after the tutorial. After finishing the recording, I will go and change this value to 0, because this is what is required here. You see, that is a good example of the way you have to go through this. You see, it's all about equations and planning, and sometimes it's difficult to find what is wrong. But what I can tell you is that you don't have to focus your attention in the Vhdl, because you see, the problem in the end was this one. This one is the wrong value here. It has to be 0, 0. I did it that very fast and I went wrong. So it's 0, 0. So let's correct that in the quartus. So now that I know, you see, this is a 0. You see the values, you may mention that, the values deduced inspecting the tables, the truth table. So LL 0, 0, that is the connection. So now is your turn to save and recompile all. So now the machine will generate a very similar circuit, but the value is going to be different. Instead of a 1, it's going to be a 0. So let the machine work for a while. Okay. So another analysis and synthesis is underway. So you see, it's not the quartus where you have to pay attention, but in your schemas, I insist on this because this is where you as a team can be working together. For example, me, myself, has been a long time, some minutes. I've got some minutes to detect this mistake because it looks pretty the same. It looks right. So I had to go and check that with the corresponding table alone. You know, if you work in groups, you realize better what is wrong. For example, the name of the chip or a value, or you see, if you have GI not, if this is what you need and you type in GI, you know, a not is missing. So perhaps you take a long time to detect that missing of a not, but your colleague, your teammate, can do that faster than you. So this is the way it works. So in the end, you have 0 errors, you have a new synthesis. So finally you can go to the model sim, and now because the simulation is running, the simulation is on the previous design, so now you finally say such a thing as restart. What is what you like to restart? Let's say everything. Okay, so now the machine will restart and you rerun the simulation. Run, I don't know, 700 microseconds, the same as before, and now click again, and now let's see if the problem has been corrected. 1, 1, it's okay. 0, 0 is okay. And now what is happening here? 1, 0. You see, 1, 0 is 1, 0, 0, perfect. And now this is what we have to check. 0, 1, whatever the value here, you see 0, 1 means that A is less than B. So yet the same value. So yes, sorry, I forgot to do something, which is I restarted, but there is, I have to, you see, it's a tricky thing, this thing. You have to end the simulation and start again. Sorry, because to take the new files, you see the question mark there. So one file was, changed. So you have to simulate again. Restart the simulation. Let me see. Start simulation. What? The new version of the files. Okay. I mean, you can restart if you add new values in the test bench, but you have to end the simulation and start again all over again if you are redesigning the circuit. And I had to redesign the unit and the test. So add to wave, everything in the region. So you can save this waveform, and then you only have to load the waveforms again. So something like this. So now run 700 microsecs, and now let's see what happens here. Let's zoom the full window, the full list of stimulus, and now let's see. 1, 0, very well, and now 0, 1, 1, whatever, 0, 1, now, yes, it now has been corrected. So you see the error has been detected and corrected. So theoretically, if you are a test engineer, you have to do that for the 32 possible situations. And naturally, you have to do that then automatically using asserting instructions in Vhdl and things like that. But now you see the lesson is okay because we had a mistake, and the mistake has generated a wrong answer. So we had to come backwards and see what happened with the schema, not the Vhdl, the schema, and we had corrected it. So in the end, everything is fine. Okay, guys? So now is simply type. Now it's the time to the same. Capture the screen, which is the object of interest. You capture the screen, and now you can save that, and well, you can add here arrows and text and whatever you have in mind, right? So that's all. That's all. 1, 2, 3, 4. So in the end, we've been testing successfully the design that this time was a comparator 1-bit solved in a very particular architecture, a hierarchical architecture based on the method of multiplexers. Just one way, like many others, to invent circuits. Okay? So that's all. Thank you.